Hello, today is the big video on derivatives. Yeah. So we're going to cover a lot in this video. We're going to cover what some derivative rules are for differentiation. We're going to go over implicit differentiation. We're going to cover some trig derivatives, and yeah, I think that's it. So let's get started. First thing, I want to make a note about differentiability that I failed to mention in the intro to derivatives video. In order to be differentiable at a point, we need to be able to find the slope. So for example, the function 1 over x, which looks like this, notice how at x equals 0, the limit from the right doesn't equal the limit from the left. We get positive infinity, negative infinity. What is going on? What does the slope look like at this point? Well, we just say it's undefined. Similarly, think of the absolute value of x, which is going to look something like this. We have a corner here. That corner is not, what's the slope there? Is it this? Is it that? Is it this? We don't, there's not a good way to differentiate at a corner. We can still take the derivatives of these functions, but it's, you got to keep in mind what the, where it's differentiable. As a general point, if there's a discontinuity, there is no differentiability at that point. So with that little note, let's get into it. All right. So we're gonna go over some basic rules. Okay, so firstly, if you take the derivative of a constant, that's going to be equal to 0. That's just a general rule. If you take the derivative of a constant, it's 0, and that's that. Let's see. Next, and you're going to love this one. This one is called the power rule. And the power rule just says that if you have some function, some like polynomial essentially, x to the n, the derivative of that is n x to the n minus 1. We'll go over some examples using these rules here in a second, so don't worry too much. That's the power rule. I should also note, I forgot to mention, that if you have d dx of c f of x, this is equal to c d dx of f of x. So you can pull constants out, take the derivative, and then just multiply back by the constant. All right, so with that, now we have the product rule. Which, so we're going to define, I'll write it over here. U and V are functions of x. Just as a note. So the derivative with respect to x of u, v, so you have two functions multiplied by each other. The derivative of that is going to be equal to the derivative of the first times the second plus the derivative of the second times the first. And it's that simple. Again, we'll go over some examples here in a second. Similarly, we have what is called the quotient rule. So if you have d dx of u over v, the derivative is going to be equal to u prime v minus v prime u all over v squared. So that's the quotient rule. What else we got? The chain rule. This is a huge one, and this is where derivatives get, on one hand, they get really fun, but also tricky. And you can have long chained out derivatives. So this is the chain rule. The chain rule says that the derivative of a function, you have a function that has a function inside of it. So think, I'll give an example right away of this one so you can make sense of it. But think like the square root of sine of x. So you have two functions here. You have square root of x and you have sine of x. And when we differentiate this, there's going to be a chain rule, and that's this right here. So it's going to be equal to f prime of gx times g prime of x. So you start with the outermost function, take its derivative, and leave everything on the inside the same, and then you multiply by the derivative of the inside. And so what you can notice here is, let's say there's, let's say you have something like, well, I'll go over an example to help that make sense. Okay, so with these rules out, we're gonna go over some, push these chairs in, give myself some space. We're gonna go over some examples. All right, let's go over example 1. We'll say d dx of 2. So using rule number 1, the answer to this is simply 0. d dx of 2x. So using the power rule, this is going to be equal to, so this is 2x to the 1, right? So it's going to be x to the 1 minus 1 times 1, and then we have the 2 as well. So what is this? This is going to be 2 times 1 is 2 times x to the 0 is 1. So this is just 2. Okay. 3. Do that. So with this problem, you could distribute everything out, and you could have a polynomial, and you could use the power rule. Oh, there's a rule I forgot to write down. We'll just write it right here. Bonus rule. It's just a helpful tip. The derivative of u plus v, oh wait, maybe I already wrote this. No, I didn't. Okay. Is equal to the derivative of u plus the derivative of v. So this can help you with, like, it's like an algebraic tool basically to help you simplify derivatives. Anyways, we could distribute this out and take the power rule and do all that, or we can use the product rule. We're going to go ahead and do that. So this is going to be equal to derivative of the first, which is going to be 3x squared times the second, which is x plus 1, plus the derivative of the second, which would just be 1, times the, so this. There you go. And I'm just going to leave it like that, but that's an example of using the power rule. Or not the power rule, the product rule. Quotient rule, I won't give an example of the quotient rule, but I encourage you to try one out for yourself. For example, let's see. Example, try x squared over x plus 1. Try that for yourself. And then we'll do the chain rule. Okay. For this one, I'm going to give a note that d dx of natural log of x is equal to 1 of x. So this is a note. You don't know this yet. Now you know it. So there's your note. With that said, we're going to take the derivative of natural log of x squared. And so what this is going to be is you're going to take the outermost function, which is like x squared, right? And so you're going to have 2 natural log of x, and then times the derivative of what's inside. So times 1 over x. There you go. So those are some examples of most of the basic rules. All right, from here we're going to go into just covering some of the trig derivatives and also implicit differentiation. Now you might be wondering why I don't cut me erasing out of the videos, and the reason is I don't know how to edit videos, nor do I don't think I have any editing software or anything. So I just post it raw, I guess. Let's use a different color. All right, trig derivatives. All right, so fortunately, our lovely trig functions are cyclical, and well, some of them are. I'll explain what I mean. So let's start with sine of x, and we're going to go down here. This is d by dx. So if you take the derivative of sine of x, you get cosine of x. If you take the derivative of cosine of x, you're going to get negative sine of x. And if you take the derivative of negative sine of x, that's going to be negative times the derivative of sine of x, so it's going to be negative cosine of x. And then similarly, if you do it one more time, you get back to sine of x. So that's those 4 functions, or I guess 2 functions, but that's kind of how they work with the derivative. And then you have, let's see here, d dx of tangent of x is going to be secant squared x. Let me just, because I'm going to give you guys some more here. Yeah, okay, just double checking. So then you have d dx of cotangent of x is just equal to negative cosecant squared of x. And then you have d dx of secant x, this one's interesting, is equal to secant x times tangent of x. And d dx of cosecant x is equal to negative cosecant x cotangent x. So those are the basic trig functions. Maybe in another video I'll cover inverse trig and maybe even hyperbolic trig. But for now, these are the ones that you should commit to memory. And now that we know some of these trig functions, I am going to do one example just to show you how, once more, how the chain rule is really powerful. Okay, so if we want to take the derivative of, let's see, we're going to have natural log of sine x squared. So notice now we have three functions, right? We have the x squared function, we have the natural log of x function, and we have the sine of x function. So to solve this, we're going to start on the outside. So there's going to be 2 times natural log sine of x times, all right, let's move to the next, so we have natural log times the sine of x, or sorry, natural log of sine of x. So the derivative of natural log is 1 over x, so we're going to have 1 over sine x. And then the derivative of sine of x is cosine of x. Let's simplify this. This is going to be cotangent x, so this is going to be 2 natural log of sine of x times cotangent of x. And there you go. So again, you can see, I encourage you, one way that I really learned derivatives is I would just create the most ugly, like disgusting function ever, and then I would take its derivative. So I encourage you to play around with the chain rule, and within probably 30 minutes to an hour, you'll have a really good grasp of it. And with that, I'm just going to briefly mention something called implicit differentiation. So this is what we've been doing is we've been saying, okay, we have a function y is equal to some function of x. And so dy dx is equal to f prime of x, blah, blah, blah. Well, now what we're going to have is we're going to have some function of xy is equal to a constant, and we're going to have to get our dy dx form. So a good example of this that I'll work through here is the equation of a circle. This would have radius 5, right? And let's say we want to know the slope of this circle at the point 3, 4. Make sure that's a point on there. Yep. So we want to know a, what is the slope, the instantaneous slope, the derivative at the point 3, 4? Question mark. Okay, so what we're going to do is we're going to take d by dx of x squared plus y squared is equal to d by dx of 25. So this is going to become 0 because it's a constant. This, so let's take, and we can split it up. So we're going to have the derivative of x squared is going to be 2x. We're going to add, and I'll just do this for now. Now, what is this? This is implicit differentiation. So the derivative of y squared with respect to x, well, we know it's going to be 2y, but then it's going to be, we're going to have to be left over with whatever the derivative of y is. And we don't know what the x derivative of y is, but this is assuming that y depends on x. And from the polar coordinate equation for a circle, we actually know what it is. But anyways, so we get this. And if you may have already seen it, we can actually use algebra to isolate dy dx. So let's do that. So now we have 2x plus 2y dy dx is equal to 0. So what this means is that dy dx is equal to negative 2x divided by 2y, which is just going to be negative x over y. And that's our answer. Now this is super convenient for our circle here, because now we can get the derivative at any point. All we need is the x and the y coordinate of that point, and we can get the slope. So on our circle of radius 5, and at the point 3, 4, which I guess would be here if we're drawing a triangle, 3, 4, right? At this point, the slope dy dx is going to be equal to negative 3 over 4. Voila! That's implicit differentiation. I might have another video at some point going a little deeper into it, but for now this should give a good intuition as to what's happening. Really, again, the magic of what implicit differentiation is happening right here. This is the big piece, and it's important to know how to do this so that you can get useful information like this. Yeah. Well, thank you for watching this video. I hope you're able to learn a lot from this. Again, watch over it, take notes, and I encourage you to create your own practice problems. It's a really good way to learn calculus in general. All right, thank you. Bye.